Hello students, myself Professor S.G. Hiramat from Department of Civil Engineering, KLS VDIT, Halia. Students, in the last class we have discussed about the three topics, that is wet weather flow, factors affecting the wet weather flow, and third one, how to estimate the wet weather flow, that is WWF. Today we'll discuss about the two topics, that is will first of all will solve few numerical problems on the estimation of storm flow, and also will discuss another topic, that is time of concentration. Students, these problems as well as the topics are very important in sanitary engineering, in municipal services, and also in the design of STP. Now, the numericals may be asked like this. So, the first one is work out the ratio of DWF, that is dry weather flow, and WWF, that is wet weather flow of a city having the following particulars. Area, it is given as 30,000 hectares. Water supply rate, it is given as 200 liters per capita per day, that is 200 LPCD. And population, it is given as 18 into 10 raised to 5, and intensity of rainfall they have given it as 15 mm per hour. Average impermeability factor they have given it as 0.5, and also they have asked to assume that 60% of water supply reaches the sewer. That is, also they have asked to comment on your results. Come to the solution. First part, that is how the dry weather flow is calculated. So it is nothing but the multiplying the population with the rate of water supplied. So that is nothing but we have to assume that as 60%. So therefore 18 into 10 raised to 5 into 0.6 into 200 liters per day. So that works out to be 2.50 meter cube per second. So this is the quantity of dry weather flow. And come to the wet weather flow, how to calculate the quantity of wet weather flow. So that is using rational formula, that is given by Q is equal to A into I into R divided by 360, where Q is runoff in meter cube per second, area in hectares, so that is given as 30,000 hectares, and I is equal to impermeability factor, so that is given as 0.50, and R is intensity of rainfall in mm per hour, so that is given as 15. Now substitute in the above equation, that is Q is equal to 30,000 into 0.50 into 15 divided by 360, so that works out to be 625 meter cube per second. So this is the quantity of storm runoff. So you can find the ratio easily, that is DWF divided by WWF is equal to 2.50 divided by 625. So that works out to be 1 divided by 250. So you can comment on this, like as this ratio is on very low side, it will not be desirable to adopt a combined system of sewerage. Hence, a separate system of sewerage should be recommended in this case. Similarly, a problem may also be asked like this. A city is having catchment area of 6,000 hectares and population density of 150 persons per hectare, is supplied with water at the rate of 200 LPCD. The intensity of rainfall is 40 mm per hour and average runoff coefficient is 0.50. If 75% of water supply contributes to the sewage, determine the design flow for a combined sewer. Assume the peak discharge factor as 3. Now come to the solution. So just write down the given things here. So area, it is given as 6,000 hectares. Intensity of rainfall, that is R, it is given as 40 mm per hour, and average runoff coefficient they have given it as I is equal to 0.50. Now easily we can find the quantity of dry weather flow, that is DWF, that is equal to total water supply into percent of water contributing to sewage. So that is total water supplied is calculated by multiplying the rate of water supply into population, that is 150 into 6000 into 200 into 0.75 divided by 24 into 3600. So that is to express in terms of liter per second. It works out to be 1.560 liters, sorry, 1560 liters per second. So if you convert that in meter cube, that is just divide this by 1000 to get 1.56 meter cube per second. So they have asked to consider the peak discharge as 3. Therefore peak discharge, it is equal to 3 into 1.56, that works out to be 4.68 meter cube per second. So therefore using rational formula, you can find the total wet weather flow, that is also known as storm water flow. So that is using rational formula, that is Q is equal to A into I into R divided by 360. If you substitute all the given values, you can find the total storm water flow here as that is 333.33 meter cube per second. So therefore design flow, that is nothing but the addition of DWF and WWF. So it is nothing but 4.68 plus 333.33, that works out to be 338.01 meter cube per second, and it can be considered as 340 meter cube per second. So therefore we can conclude that the combined sewer can be designed by considering 360 meter cube per second. Now come to the today's second topic, that is time of concentration. First of all, we'll discuss about the meaning of the term. This term is used in connection with the design of stormwater drains. As the rain falls on the ground, all the area to be served by the sewer does not start to contribute immediately to the flow of sewer, but the flow is built up gradually as follows. First one is the area just near the sewer line will start contributing first, and it will go on increasing as more and more area starts to contribute. Secondly, when the whole area is contributing to the flow of sewer, the maximum limit of flow will be reached, and it will be equal to the rate of precipitation of rain water. Third one, the maximum flow continues until the storm stops. The flow then gradually falls down as the area near the sewer line stops contributing firstly, while flow continues to come for considerable time from the distant area. The total time required by the flow to reach to the maximum limit is known as the time of concentration, and it consists of two parts. So that is, first one is A, that is time of entry, and B is time of flow. Now we'll discuss in brief about these two terms, that is time of entry. The time required by storm water to reach to the uppermost inlet of the sewer line is known as the time of entry. The value of time of entry depends on many circumstances, the chief being size, shape and slope of area. The various authors have given different values for time of entry. Lloyd Davis gives time of entry for paved surfaces as 1 to 3 minutes. According to Horner, time of entry is about 2 to 5 minutes, and according to Metcalf and Eddy, it is about 3 to 20 minutes. Appleby has recommended time of entry for 7 to 15 minutes. Thus, extreme care is to be taken to assume the proper value of time of entry. Generally, the time of entry for paved surfaces is taken as about 1 minute for every 6 meters length. The time of concentration is worked out by using the following formula. So this is also empirical in nature. So that is Tc is equal to 0.885 L raised to 3 divided by H whole raised to 0.385, where Tc is time of entry in hours, TE is time of entry in hours, L is length of overland in kilometers for farthest point to the inlet point of sewer, and capital H is equal to total fall of level in meters from the farthest point to the inlet point of sewer. Now second part is time of flow here. The time taken by the storm water to flow down to the sewer up to a particular point is known as the time of flow, and it depends on length, size, slope and smoothness of sewer. So time of flow, the time taken by storm water to flow down the sewer up to a particular point is known as the time of flow, and it depends on length, size, slope and smoothness of sewer. The time of flow can be easily determined by applying the principle of hydraulics. If the velocity of flow and distance to be traversed are known, the time of flow can be determined by the relation, that is time of flow, that is TF is equal to distance to be traversed divided by velocity of flow. The addition of time of entry and time of flow gives the time of concentration, that is T. So mathematically I can say time of concentration, that is capital T, is equal to TE plus TF. So what is the importance of this time of concentration here? The importance of time of concentration in the design of storm water sewer lies in the fact that out of all storms of equal frequency of occurrence, that storm which has duration equal to the time of concentration produces the maximum flow in sewer. This statement can be understood by taking an illustration here. Now, by solving the example, you will come to know the importance of this time of concentration. The problems may be asked like this. The drainage area of one sector of a town is 12 hectares. The classification of this area is as follows. So they have given the percent of total surface area, and also they have given the types of surface, and also they have given the coefficient of runoff. So if you consider 20% among the given area with hard pavements with a coefficient of runoff as 0.85, and 20% consists of roof surfaces and the runoff coefficient is 0.80, and 15% unpaved street and the coefficient of runoff is taken as 0.20, and 30% garden and lawns and the coefficient of runoff will be 0.20 because there will be percolation of water into the ground. And also they have given that 50% of wooded area and the runoff coefficient or coefficient of runoff can be taken as 0.15. And also they have given if the time of concentration for the area is 30 minutes, find the maximum runoff. And also they have suggested to use the formula, that is R is equal to 900 divided by T plus 60 for the calculation of rainfall intensity. Now come to the solution part, that is if A represents the total area, then we have K1A1 is equal to 0.85 into 0.20 into A, that works out to be 0.17A. Similarly, you can find K2A2, K3A3, K4A4, K5A5 and sum up all those areas, and summation it is equal to 0.4425 A. Now K can be calculated, that is summation of Ka divided by A, so that is nothing but K is equal to 0.4425. Now in the formula of the type, R is equal to 900 divided by T plus 60. R is the rainfall intensity generally expressed in mm per hour, and T is the concentration time in minutes. So R can be found out using the relation, that is R is equal to 900 divided by T plus 60. So that works out to be 10 mm per R. So that is equal to 1 centimeter per R. Now, PC to be used in our rational formula, that will be equal to 1 centimeter per R. Now, using the rational formula can also be written in the form, that is 1 divided by 36 kpc into A, where just you substitute all the values to get the QP as 0.1475 chemex. Say it as 0.148 chemex. Therefore, the maximum rate of runoff expected from the area will be 0.148 chemex. Let us solve another numerical in which the data are given like this. A population of 30,000 is residing in a town having an area 60 hectares. If the average coefficient of runoff for this area is 0.60 and the time of concentration of the designed rain is 30 minutes, calculate the discharge for which the sewer of a proposed combined system will be designed for the town in the question. Make suitable assumption where needed. First, come to the solution part. First, assume per capita water supply as 120 LPCD. Assume 80% of water supplied will be reaching sewer as sanitary sewage. Therefore, the quantity of sanitary sewage produced per day will be equal to 2880 cubic meter. Quantity of sanitary sewage produced per second, so that is equal to 2880 divided by 24 into 60 into 60. So that works out to be 0.033 cumex or meter cube per second. Now the average sewage discharge will be 0.033 cumex. Assume maximum sewage discharge to be 3 times the average sewage discharge. Therefore, the maximum sewage discharge will be 3 into 0.033, that works out to be 0.1 cumex. The storm water discharge, so can be calculated using the rational formula once again. So put all the values in the rational formula, so that is to get the storm runoff as 2.1 cumex. Assuming that another numerical we are going to solve. In the numerical, they have given the data like this. Assuming that the surface on which the rain falls in a district is classified as follows. 20% of the area consists of roofs for which the runoff ratio is 0.9. 20% of area consists of pavements for which the runoff ratio is 0.85. 5% of the area consists of paved yards of houses for which runoff ratio is 0.8. 15% of area consists of macadam roads for which runoff ratio is 0.40. 35% of the area consists of lawn, gardens and vegetable plants for which the runoff ratio is 0.10, and the remaining 5% area is wooded for which the runoff ratio is 0.05. Determine the coefficient of runoff for the area. If the total area of the district is 36 hectares and the maximum rain intensity taken as 5 cm per hour, what is the total runoff for the district? So this come to the solution. So as we did early in the previous problem, just to multiply the each area considering the percentages. So that is to determine the that is value of k as 0.4875. So therefore runoff factor will be 0.4875. Peak discharge, just to substitute all the given values in the rational formula. So that is to get the peak discharge of storm flow as 2.55 cumex. So this is how we can estimate the storm runoff as well as dry weather flow by knowing the rainfall intensity as well as impervious factors, etc. And also by knowing the water supplied, we can find the dry weather flow. Thank you, students.